Hello, welcome to lecture 28 of the course. This is lecture 7 of module 3. In this lecture, we will discuss the classical counterpart of Langevin noise, that is quantum Langevin noise. And finally, we will begin our discussion on the effect of quantum noise on an optical mode in a Fabry-Pérot cavity, as Fabry-Pérot cavity is the backbone of a cavity optomechanical system. So let us begin. In the last class, we continued our discussion on modeling a realistic situation regarding the interaction of the system harmonic oscillator with the surrounding. The surrounding was modeled as a collection of independent harmonic oscillator and harmonic oscillator, each having different coupling coefficient or coupling constant, and our analysis ultimately led to an equation of motion for the damped harmonic oscillator, and we got a memory function defined as this quantity gamma of t, and on the right hand side of the equation we get a parameter called xi of t, and this is the so-called Langevin noise. And this memory function was simplified defining a function called Bath spectral density, denoted by the quantity j of omega, and using this memory function can be written in this particular form. And in fact, for many practical cases, this Bath spectral parameter can be taken as mass into the mechanical damping gamma m into omega. This is known as the ohmic damping. So under ohmic damping, this memory function will take this form. In fact, ohmic model results in a damping that does not depend on the previous history of the bath. It does not depend on any earlier time, and therefore this process is known as the Markovian process, and we obtain these equations here. Now on the right hand side of this equation we have this Langevin noise, and this is a signature of the this is actually also called thermal force, and this clearly shows that unlike the other case when it is zero, in that case transfer of energy can take place from the harmonic oscillator, system harmonic oscillator to the surrounding, but not from the surrounding to the system oscillator. So here presence of this Langevin noise says that both process is possible. That means transfer of energy from the system oscillator to the surrounding and back from the surrounding to the system oscillator, and thereby the system will come into a thermal equilibrium. Then we went on to calculate the Bath correlation function, and this xi of t, as it is the Langevin noise, so we and it is related to the Bath, and we try to calculate the first moment, that is average of the Langevin noise, and its autocorrelation function, that is the second moment. So here what we assume that the system Bath coupling is weak, and then this Langevin noise expression become a little bit simplified, and our calculation led us to the fact that naturally the expected or the average value of the Langevin noise is 0, and the Bath correlation function we calculated, and in the process we learn how to calculate the average value of various quantities, and it turns out that the this second moment or the autocorrelation function for the Langevin noise is a expression like this, and it physically it says that each interaction of the Bath with the system oscillator via the Langevin noise is correlated only to itself and not to any other interaction, and also the strength of the fluctuation varies directly with the mechanical damping parameter gamma m, which is again related to the so-called fluctuation dissipation theorem. And we went to recall the Wiener-Khinchin theorem, which we discussed in the context of movable mirror in an earlier class, which basically says that the noise spectrum is a is nothing but the Fourier transform of the correlator, and in analogy to this we have written down the noise spectrum for the BAT, and which is known as the spectral noise density, and that is the Fourier transform of the second moment of the Langevin noise, and we worked out that this for ohmic damping, this turns out to be a very simple expression, and it is independent of the frequency for ohmic damping, and that's the reason that in the case of ohmic damping, the Langevin noise is said to represent the so-called white noise. And this Langevin noise can be expressed in the frequency domain also, just by taking the Fourier transformation. Then we are started discussing the quantum regime. To discuss quantum regime, we now have to calculate the expectation value of various parameters. So we and because we are considering a collection of an independent harmonic oscillator at some temperature T, so we written down the density operator for the system, and that will be required because we know that when we take the average of any quantum optomechanical operator, expectation value is given by the trace of the rho density operator into the operator. So this has to be calculated. So we worked out the thermal density operator for these thermal oscillators in the thermal state, and we calculated the average phonon number because these are thermal mechanical, we are modeling it as an oscillator and having in the thermal environment, we term it the quanta is termed as phonon there, and we use the symbol B to represent this phononic oscillator, and we calculated the average value of phonon number, which is the usual, this is the familiar expression we obtain, and then we try to calculate the position correlation for an ensemble of n harmonic oscillators, and we finally obtain this particular expression. Now we are going to build up our next analysis from here. Only thing, let me remind you that you should understand this, the notation here, this bracketed nk represents this one, so it's a collection of all n1 n2 up to n capital N number of items we have there, and this ket represents the direct product of various number state corresponding to the oscillators. Let us now write the position operators. This qi, qj, these are operators. Let me write qi is equal to, I am not using the this operator sign, but you please understand that I am now talking about operator because now we are in the quantum regime. So qi is equal to qi0 plus bi dagger. This is the position operator for the ith oscillator, and here qi0 is equal to, this is the 0 point fluctuation, this is h cross divided by twice mi omega I. Mi is the mass of the oscillator, ith oscillator, and omega I is the corresponding resonance frequency. Now, by the way, please recall that we have utilized similar thing earlier when we have this displacement operator x. In this we wrote earlier in the context of when we discuss about harmonic oscillator. This is x 0 point fluctuation, and there we used a plus a dagger. Now x 0 point, this fluctuation was defined as h cross divided by twice m omega. The same thing here we are doing it, and we can then also write for qj. For qj we have qj0 for the jth oscillator, bj plus bj dagger, and here qj0 is equal to h cross divided by twice mj omega j. All right, now we have to calculate this particular quantity. So let us do that. First of all, let us calculate this bracketed bra of these number states qi qj, and this ket. Basically we are calculating the scalar product for this operators, product of these operators qi qj. Now if I put qi qj, I have qi0 qj0, and this is actually, I can write it as n1 n2. These are the direct products up to nn in shortened notation. qi qj, if I break it up, so I will get 4 terms. So those would be bi dagger bj plus bi bj dagger plus bi dagger bj dagger, and we'll have bi bj, and then on the other side you will have n1 n2 up to capital N number of oscillators. So we'll have the corresponding quantity for that, and you will see that the contribution from these two terms, this term as well as this term, is obviously going to be 0. Just recall to understand it, we can calculate, say, nbb or nb dagger b daggers. You can do that also. Then here you will see, you will get it as, your simple calculation will give you it as n minus 1 into n minus 2. All right, and you will have here n minus 2, and these are orthogonal, so this would be 0. So these two contribution would not be there because of these two terms. So I will simply have qi0 qj0 n1 n2, say ni nn, and here you will have bi dagger bj plus bi bj dagger, and the other side you will have, say, n1 n2. Let me take it. So this anyway you have understood. This one, let us say I have nj up to nn. Okay, so now let us proceed further. So let me calculate it term by term. So I have qi0 qj0, I have here n1 n2. Okay, so here this, let me first consider this particular term. So bi dagger bj. So bi dagger, when it this operator operates on the bra ni here, it will operate on only the nth oscillator. So it would become, because it is bi dagger operating on this would become, ni minus 1, and then you will have up to nn, and this will give you square root of ni. Similarly, when bj operates on nj, you will get nj, square root of nj, and here you will have n1 n2 and so on up to, say, it will, nj would become nj minus 1, and you will have nn. So this is what you will get from the first term. Now let us consider this term, and in the similar way here you will see that this would become n1 n2, and this ith operator bi, annihilation operator, when it operate on this, you will get, this is, you will get it as ni would become ni plus 1, and you will have nn here, and this would become square root of ni plus 1. Similarly, now bj, when it operates on nj, it would become square root of nj plus 1, and in this side you will have n1 n2, and you will have it as nj plus 1 and nn. Okay, so therefore I can write the whole thing as qi0 qj0 square root of ni nj plus square root of nj ni plus 1. Sorry, you will have ni plus 1 and nj plus 1, and then I will write it as delta ij because all the other terms will not contribute. As you see, this one, for example, ni minus 1 and nj minus 1, they would become orthonormal. It will get normalized provided I is equal to j. If I is not equal to j, then they will vanish, because scalar product with n1, because this is just a number, n1 and n1 will give you 1, n2 and n2 will give you 1 scalar product, but ni minus 1 and nj minus 1 will give you 1 provided I is equal to j. Okay, similar is the logic for this particular second term also. So therefore we will end up with this particular expression. So therefore we have evaluated, let me write it again here. What we got is, we have evaluated this particular quantity, and we have qi, qj, scalar product we have worked out, and this is, we got qi0, qj0, square root of ni nj plus square root of ni plus 1 into nj plus 1 delta ij. Okay, now let us proceed further. We have, ultimately we have to work out the expectation value of this product of these two operators, and this is equal to, we have summation. So let me show you the expression once again here. So this we have to have, let me write here again, we have summation over all these nks, and this is product, and p and k, qi0, qj0, this already we worked out. So just let me copy from here this same term we are having here, let me put it. Okay, all right, let me do it let me write here. So qi0, qj0 plus square root of ni nj plus square root of ni plus 1 nj plus 1 and delta ij. Okay, now let us do one thing. Let us look at separate the terms where k is not equal to I. So we'll separate it terms like this. Say when nk is not equal to ni, and that means k is not equal to I. Here I have p and k, this term, and concentrate only the ni terms here. And when nk is equal to ni, so we have here p ni. Okay, and I have qi0, qj0, and this term already I have ni square root of ni nj plus square root of ni plus 1 nj plus 1 delta ij. This mathematics may look little bit cumbersome, but it's actually not that difficult, but you will get a very useful result, and it is important to know how to do these calculations. Now you see this particular term will give you simply 1, because the probabilities, for example, any corresponding probabilities, you have terms like this p1 summation p2, because of this product you will have all these probabilities would be equal to 1, right? Sorry, this would be equal to 1, this would be equal to 1, this would be equal to 1. So overall you will get, from here it will be unity, the whole thing, and therefore I will be left out with only this term. So let me write here, you will have summation ni, pni, qi0, qj0, and square root of ni nj plus square root of this, again let me write here, nj plus 1 delta ij. Okay, finally, let me now sum it over all the oscillators. Finally, if I sum up, that means if I sum up over the variable ij for all the oscillators and oscillators, I have qi qj. So this would be, I can write it as ij, and here I have ni, and it is this particular term. Okay, let me put it here. Okay, I have to write it again. So I will have qi0 qj0 square root of ni nj plus this one nj and delta ij. Fine, so this you can easily evaluate. Because of this Kronecker delta, I put I is equal to j, then I'll be left out with only one summation. This is basically two summations are there. Now we are having one summation, and then this summation over ni variables, ni's, and then qi0 square, and I will have, I think I missed this term here, that is pni has to be also there. So let me put it here. So I have pni, or rather let me write it this way. Okay, then I have this term pni is also I have to write. Okay, so I have here pni. Now because I take I is equal to j, I will have qi0 square, then I have pni. So from here I will get ni, and from here I will get ni plus 1. So this will give me 2 ni plus 1. This I can further write as this. I can write it as summation I qi0 square, and this would be twice n of omega I. I'll explain how I'm getting it. So this is what I will have here. This n of omega I is nothing but the average number of phonons for the ith oscillator, and that is ni pni. I think this you can recognize. I have just utilized this one. So this is the expression I get. Now therefore this is a very important result I obtain. Ij, when I take the summation qi qj, this is what I got. This one I can further simplify, because I know that n of omega I, this already we worked out, and this is equal to e to the power h cross omega I by kbt minus 1. And if you put it here and do the analysis, you will get it as this quantity position correlation term would turn out to be very straightforwardly. You can work it out. I encourage you to do it. Otherwise maybe we can do it in the problem solving session. It's just simple algebra. You will get cot hyperbolic h cross omega I by twice kbt. Okay, so this is what we obtain. We will now discuss the quantum Langevin noise in the similar line as we did for classical Langevin noise. Now both the system and the Bath oscillator variables are now quantized, and they follow this commutation relation. Say qi pj, this commutation is equal to I h cross delta ij. The Hamiltonian for the system and Bath combined together is now written in this form. So this is exactly the same as you will see, except that now the position variable and the momentum variable are replaced by the corresponding operator. So this is the system part. We have p square by twice m, that's the kinetic energy. Then I have this potential energy of the system oscillator, m omega m square q cap square, the operators. Then these bars are considered to be a collection of n quantum harmonic, independent quantum harmonic oscillators with the corresponding momentum variable, say pi for the ith oscillator, mi is the mass of the ith oscillator, plus this potential energy term half mi omega I qi cap square, and then the interaction between the system and the Barth oscillator is given by this particular term. This is exactly what we wrote for the classical case as well, and then we have this term is taken added there to take into account the cancel the effect of shifting of the frequency of the system oscillator. So we have this term ci twice mi omega I square. Okay, now using Heisenberg equation of motion, we'll again get equation of this form, exactly the classical equation we get, but now it will be in the operator form, mq double dot plus m omega m square q plus m gamma m q dot, that is equal to the Langevin noise. Now this Langevin noise term is then operator. It is written in the operator form, where this is same as in the classical case, only it is the variables are now replaced by its operator. So assuming that the coupling between the Barth and the system to be weak, then I can write this as this one, qi cap cos omega I t plus pi cap 0 mi omega I sine omega I t. Okay, now it can be very easily verified that this Langevin noise operator, quantum Langevin noise operator, is Hermitian. So xi of t is equal to xi dagger of t, and also you can show that because of the commutation, you will see that xi of t, xi of 0 is not equal to xi of 0 and product of xi of 0, xi of t. Now we can calculate the autocorrelation function for the quantum Langevin noise. That is, we have to calculate xi of t, xi of 0, and this would be in the similar line as in the case of the classical case. Let me first write the whole term ij. I have here ci, cj, and we'll have qi of 0, qj of 0, the expectation value of the product. Then I have cos omega I t, cos omega j t dash. I will have 4 terms, so let me write all of them, and I will have expectation value of all these are operators. I'm not writing the operators sign, but you please understand that these are all operators. So I have qi 0 here, pj of 0 here, divided by mj omega j cos omega I t sine omega j t dash, and then I have plus pi 0 qj 0 divided by mi omega I sine omega I t cos omega j t dash, and then plus pi of 0 pj of 0 divided by mi mj omega I omega j sine omega I t sine omega j t dash. Alright, so this is what I'll have. Now just a while back we have calculated these quantities, say qi 0, these are operators again. We calculated qi 0, average expectation value of this product of these two operators, that would be that we calculated as summation over ni pni qi0 qj0, and we have it as square root of ni nj plus square root of ni plus 1 nj plus 1 delta ij. Okay, and similarly you can show that you will get for this pi0 pj0, that would be equal to summation ni, you have pni pi0 pj0, and this is the same, it is square root of ni nj plus square root of ni plus 1 nj plus 1, and you have delta ij. However, here this pi0, similarly for pj0, that would be h cross mi omega I by 2 square root, or pj0 is equal to h cross mj omega j by 2 square root. Now using these relations we can work out the autocorrelation for the Langevin noise, quantum Langevin noise here, because these are now operators, quantum operators, and if the calculations are done, you will see that you will get it as summation I is equal to 1 to n h cross ci square divided by twice mi omega I, and here you will have quad hyperbolic h cross the reduced Planck's constant h cross omega I divided by 2 kbt, kb is the Boltzmann's constant, and here you have cos omega I t minus t dash minus I sine omega I t minus t dash. So this is what you will get. Again, as like in the classical case, we can define the so-called spectral density function j of omega, and that is exactly in the similar way we have it is pi into summation over all the oscillators, and I have ci square divided by twice mi omega I delta omega minus omega I. Now we can rewrite the autocorrelation function for the Langevin noise in terms of the spectral density function as this xi of t dash. This should be equal to, you can just put it and you will get it as h cross by pi 0 to infinity. You please look into the classical case once again and you will get it. It will be h 0 to infinity d omega j omega quad hyperbolic h cross omega by 2 kbt cos omega t minus t dash minus I sine omega t minus t dash. Alright, so this is what you will get. Now as in the classical case, here also let us go for ohmic damping because we are interested in Markovian process. So for ohmic damping, if we consider ohmic damping where this spectral density function is given as mass into gamma m omega, we obtain the autocorrelation function expectation value of xi of t dash, that would be equal to m into gamma m divided by pi integration d omega h cross omega quad hyperbolic h cross omega by 2 kbt cos omega t minus t dash minus I sine omega t minus t dash. Okay, Now here this integration limit is from 0 to, generally we write infinity, but to be precise there is some cutoff frequency is there for ohmic damping, that is omega c, and it is generally taken in the limit say omega c tends to infinity. Now in the first approximation, in the classical limit, you know that in the classical case h cross tends to 0 and temperature is non-zero, T is non-zero, and cot hyperbolic h cross omega by twice kBt, this can be approximated to be, as you can actually show it, it would be 2 kBt divided by h cross omega. And if we set omega c at infinity, then you can very easily show that in the classical limit this Langevin, this autocorrelation function for the Langevin noise would be, again will regain what we got in the classical case, that is twice m gamma m kBt delta t minus t dash. Okay, so this is what we will obtain, and in fact we must get it. Now there is actually another interesting form of this second moment of the Langevin noise, quantum Langevin noise, which you will often encounter in research literature, and it's very easy to get it. What is done there, you just have to utilize these facts and you can immediately rewrite it. You know that minus infinity to plus infinity, omega cot hyperbolic h cross omega 2 kBt sine omega t minus t dash. This integration is in the frequency domain, right? So you have here d omega, so this would be equal to 0 because this overall, this integrand, this would be odd function. And another fact you can utilize is say minus infinity to plus infinity omega cos omega t minus t dash d omega is equal to 0. If you utilize these two properties, then this autocorrelation function for the quantum Langevin noise can be written in a slightly different form. That would be this. You will have m gamma m divided by 2 pi. You see here the limit is from omega c, you will put it as infinity, then 0 to infinity we can replace it by a half of, that's why this 2 term is coming. Here we had m gamma m by pi, so I will have a half term here because now I am taking the limit from minus infinity to plus infinity, so that I can utilize these two properties there. And what I will have is this. You will have it as, it's very simple and straightforward, you can verify it, d omega h cross omega cot hyperbolic h cross omega by 2 kBt. Then rather than writing here you have this cos, so I will write here e to the power minus I omega t minus t dash, because the sine part will give me 0, that's why I can do it. And for the second term, that means this particular term, in the similar way I can utilize this particular property, and then I can write it as minus infinity to plus infinity d omega h cross omega e to the power minus I omega t minus t dash, and this is what I will get. Or in short, I can write it this very useful expression which you will encounter in many research literature or research paper. It would be simply h cross m gamma m minus infinity to plus infinity d omega by 2 pi e to the power minus I omega t minus t dash omega cot hyperbolic h cross omega by 2 kbt plus 1. Okay, I'm just simplifying this expression, and this is very popularly and very frequently used the second order moment or the autocorrelation function for the quantum Langevin noise. You can see that autocorrelation function depends only on the time difference tau. Say time difference, let me denote it by tau, that is tau is equal to t minus t dash, as you can see from this term here. So because it depends on the time difference only, therefore this quantum Langevin noise xi of t is called stationary, and therefore we can in fact write it in this form also, this autocorrelation function xi of t, xi of 0, that would be equal to m h cross gamma m integration minus infinity to plus infinity d omega by 2 pi e to the power minus I omega tau omega cot hyperbolic h cross omega by 2 kbt plus 1. Okay, now the Fourier transform of this autocorrelator gives us the so-called spectral noise density in the quantum domain, that would be S xi omega, that is the Fourier transform of the autocorrelator. So xi of tau, xi of 0, and the Fourier kernel say I omega tau. We are evaluating it at for frequency say omega greater than 0 and integrating over time. Integration limit is from minus infinity to plus infinity. We can quickly evaluate it, it's very simple, so let us do that. We'll just put the expression that we have derived for this autocorrelator, that is m h cross gamma m integration minus infinity to plus infinity d tau, and here I have minus infinity to plus infinity. Let me use the frequency variable, say omega dash, d omega dash by 2 pi e to the power I omega minus, because now I have here this minus omega is here, so I'm doing it replacing by omega dash. Okay, so this is what I have. Then here I will have omega dash, I will have cot hyperbolic h cross omega dash by 2 kbt plus 1. Okay, this can be further simplified because you can recognize that what I have here is this Dirac delta function minus infinity delta function I will have. If you look at it, this expression, I have a term like this, integration d tau 1 by 2 pi e to the power minus I omega minus omega dash tau. This is nothing but the Dirac delta function delta omega minus omega dash, so I can utilize it. If I utilize it, then I will be able to write the whole thing as m h cross gamma m minus infinity to plus infinity. You will have d omega dash delta omega minus omega dash. I have here cot hyperbolic h cross omega dash divided by 2 kbt plus 1. Okay, now using the property of the Dirac delta function, I will get the spectral noise density for the quantum Langevin noise would be m h cross gamma m cot hyperbolic h cross omega divided by 2 kbt plus 1. Okay, so this is what we obtain. Sometime back we actually saw that if you have worked out that this cot hyperbolic h cross omega by 2 kbt, I can write it in terms of the average number of phonon as 2 into n omega plus 1, and just recall that n omega is nothing but the average number of phonon, and it is given by 1 by e to the power h cross omega by kbt minus 1. So if you utilize it, then you can show that this function is nothing but cot hyperbole h cross omega by 2 kbt is can be expressed in this form. And using this, we have the spectral noise density that would be, in terms of the phonon number, I have twice m h cross gamma m omega. So this I got it. Let me 1 minute. So I think I missed something here. Here I have this term omega is also there because I have used the Dirac delta function. So that's how this omega term is coming, and I will have here n of omega plus 1. Okay, so this is what we obtain for when omega is greater than 0. On the other hand, I can also work out what is the spectral noise density at minus omega, and in that case it would be integration would be minus into plus infinity d tau, the Fourier transform of the correlator I have here. And because it is omega is less than 0 in this case, so I have minus rather than plus. I have minus I omega tau. In this case I am having omega less than 0. And please do this calculation very straightforward, the way we have done it. You can show that you will get twice m h cross gamma m omega. Now you are going to get n of omega, not this plus sign would not, plus 1 would not come. So this is what you will get as xi at minus omega. So it is clear that this spectral noise density in the quantum regime is not symmetric. Okay, this is what the first thing we obtained in the what is different from the classical regime. So it is not symmetric. This spectral noise density function is not symmetric. Okay, in the classical limit, however, in the classical limit you can show, because you know that in the classical limit your h cross tends to 0 and your this kbt is much greater than h cross omega, and in that case you can have this average phonon number can be written as kbt divided by h cross omega. And utilizing this, you can show that the spectral noise density function in the classical limit would be twice m gamma m kbt, and if it is evaluated at minus omega, this will also give you twice m gamma m kbt. So in the classical domain, this quantum this is not this spectral noise density function would be symmetric. One thing we can do here, if say temperature is very high, if temperature is high but you are still in the quantum limit, say but your h cross is not equal to 0, then we can write very approximately, and this is going to be useful later on, approximately this spectral noise density function, quantum noise density function, as twice m gamma m h cross omega m. Now this n of omega is evaluated at the mechanical frequency omega m plus 1, or the resonance frequency of the mechanical system oscillator, and as I at the frequency minus omega, this would be twice m gamma m h cross omega m, you will have n evaluated at omega m. Now let us come to our Fabry-Pérot cavity, which is the main setup for cavity optomechanical system, and let us see how the quantum noise affects an optical mode. So we are going to study optical noise effects on an optical mode. This actually comes under the so-called input-output theory as well. You know that the optical mode undergoes damping inside a Fabry-Pérot cavity, and the electromagnetic fluctuation from vacuum outside the cavity inject quantum noise into the cavity. And in the case of cavity optomechanics, the cavity is often driven by a single mode laser having frequency say omega L. We will consider these environmental effects for a single sided cavity as depicted here in this schematic diagram, where one of the mirror is perfectly reflecting, say this one is perfectly reflecting, while the other one is weakly transmittive. We'll begin our analysis with a Hamiltonian that I'm now going to write in the Heisenberg picture. Let me first write down the full Hamiltonian. H is equal to h cross omega optical A dagger A. This is the Hamiltonian which denotes the energy of the optical mode in the cavity, where omega optical is the resonance, cavity resonance frequency. Then we have another term that is summation over all the oscillators, Bath oscillators, h cross omega I bi dagger bi. So this term describes the energy of the Bath oscillators. In fact, these are electromagnetic oscillators. This vacuum we are now modeling it as a collection of independent harmonic oscillators, and it surrounds this optical cavity only with the constraint that it has is that bi, this commutation relation has to be satisfied. Bj dagger should be equal to delta Ij, and then we will have another term that is, it is now driven by a laser from outside, so that is taken into account by h cross omega drive. This is the driving amplitude, and we have this term A dagger, a photon is created inside the cavity, and the laser frequency is omega L, and it should be Hermitian, so therefore there is a term Hermitian conjugate. And many times this particular term is, people write it in this form also, say IH cross omega drive, because here the drive amplitude is considered to be a real quantity, but it may be a complex quantity because it has a phase part, so people write it in this form also, omega drive A dagger e to the power minus I omega LT minus omega star this omega drive, it's complex, A e to the power I omega LT. Alright, so this is another form, and in fact it is the most general form, and maybe let us consider this particular form rather than this one here. We'll come to that. And there will be another term that would be summation over all the Bath oscillators, h cross omega I star A bi dagger plus omega I A dagger bi. So this particular term actually refers to the fact that there is a coupling between the system and Bath, and the strength of the coupling between the cavity mode and the ith Bath oscillator mode is given by omega I. So this is the usual coupling, and we'll now going to analyze it. But as I said, let me rewrite the whole Hamiltonian in this form, and this is what we are going to analyze. rather than writing omega opt, so let me just put S cross omega 0 here, that is the optical cavity resonance frequency. H cross omega 0 A dagger A plus summation H cross omega I bi dagger bi, and then let me now take the general form here, that is I H cross omega drive A dagger e to the power minus I omega lt minus omega drive star A e to the power I omega lt, and finally we have summation H cross omega I. So please don't get confused with omega terms here. This is omega drive and this is the omega I. Omega I refers to the coupling between the optical cavity and the Bath oscillator. So what this particular term says, that when a Bath a optical cavity is getting annihilated and this is getting resulted in the creation of a Bath mode, or opposite process can also happen. So this is basically is happening due to the coupling, okay, between this Bath oscillator mode and the optical mode. So we are now going to analyze this particular Hamiltonian, and this is will give us lot of insight about what's going on as regard quantum noise effect in an optical mode is concerned. Let me stop here for today. In this lecture we discussed about the quantum Langevin noise. We have worked out the autocorrelation function for the quantum Langevin noise, and also we saw that the quantum spectral noise density is not symmetric unlike its classical counterpart. And finally we started discussing on the effect of quantum noise on an optical mode in a Fabry-Perot cavity, and we'll continue this very important discussion in the next class. So see you in the next class. Thank you.